为这是编辑器方面的，但是实际上对不同的图是用不同的纸串，有特别的效果。对，而且因为它制作很简单，所以很多上动作里面很浅。
今天很高兴，很谢谢大家来今天的 Functional Thursday。然后今天然后刚好呢，因为我们前一阵子在ICHP 碰到 Oleg Kiselyov， 然后他谈一谈，然后我们就决定把他邀来台湾，然后就来跟我做一些东西。然后那其实大家应该都很多人知道他，因为他非常有名，非常厉害。大家都传说他是外星人。然后那其实然后在这2天跟他一起做事情，发现他真的非常的有效率。然后一进来就是马上我只是问了一个问题，然后他就觉得这个可以写哦，然后他第二天就写出了6、7页的 paper， 然后所以就开始改，然后之后准备要投了，吓我一跳，还是不知道那个 paper 到底在写什么。那是他知道的，然后那么总之今天他，然后在这个演讲之前，他丢了一大堆题目让我们选，每个他都可以说，然后最后今天这个题目就是我们一些人选出来说，我们有人说想要听他讲这个final tag list 的东西，所以我们就请他讲。那之后其实待会儿讲完之后也大家如果什么问题要留下来，问题要问也可以请他留下来问他，他应该都蛮乐意讲的。谢谢，先谢谢他。
Thank you. I'm very glad to be here. I never visited Mozilla before and never visited any gathering of Taiwanese programmers before. So this is my second time in Taiwan. Actually, I've been at Flolac in 2008, 6 years ago. So that's my second time here. So this is a tutorial that I gave a month ago only in British Columbia. So these are the slides. I'm not going, there's only a few slides on there. So the tutorial was, the content kind of similar, but I would do slightly different because, well, first of all, the tutorial itself was an OCaml, so I'm going to talk about Haskell today. And also the tutorial was 3.5 hours, and well, probably today it's too late if I actually go through all of this. So I hope to finish within 1 hour. But there are some interesting slides about some slides about the introduction that I was going to talk about. So the point about this tutorial is to give you an idea how to embed domain-specific languages in this style that I keep advocating. And so not only you can embed it, but you can only optimize it. So the point of the tutorials was, the academic tutorials were more about embedding, but this one is about optimizing. Because optimizing is thought to be very difficult, and then we recently found out how it is possible. And of course, it can be done in many languages. So my tutorial was in OCaml. I also gave somewhat similar tutorial in PPL, so in March this year. So PPL is the main Japanese conference for programming language researchers. So about almost everybody who is in functional programming or programming languages, PPL is called Programming and Programming Languages, attends this conference. And it's usually attendance about 150 people. So there are that many functional programmers in Japan. So usually they have all the professors, plus students, plus somebody from the industry. So it became very good. So I gave a tutorial for 15 minutes. And so this kind of similar to what's there. So I was, I don't know if it works today, I don't know, but usually when I try to give a tutorial, I would prefer that it's kind of more interactive that way, so less of the lecture style, but more me interacting with it. Well, you asking me questions, and maybe I will ask you questions, and also I will interact with the compiler over time, and then well, you can also follow along and interact with it. There was actually a link where there's some code you can actually find there, so you can interact with the compiler. but it's probably, because of the limited time and then interactivity has to be sacrificed, unfortunately. I think that you cannot, well, generally it's very difficult to pick up a skill if you don't actually do it yourself. It's one thing that you listen to me, how I do it. Yeah, of course I've done it many times before, that I can do it. The point is not me doing it, the point of you understanding how to do it and then you have to do it. So of course it was meant to be a tutorial, so it was meant to be using the example. An example was chosen so simple that I don't have to explain what the example is. So we concentrate not on an example, but we concentrate on the implementation techniques. And the example is a very, very small domain-specific language for digital circuits, so everybody knows what they are. So, but of course, it has been applied to some real application, or more realistic application. And the realistic application was optimizing, embedding domain-specific language for database queries. So it's something like SQL, but it's a more functional notation. So on SQL, usually it's not composable, so you have to write this long select statement, right? And well, you can use nested select, but then your performance goes down. So the idea was you write something in a very functional style and then eventually compile to something which is like, a big ugly SQL statement, and then you ship to the database and then the database does things. So that has been implemented, and it was embedded implemented on a camel, and then these techniques have been used. So the idea how to achieve the good performance, that after you compose the query, then you have to optimize it in many ways. So there are many rewriting rules, about 10 rewriting rules, and then it becomes a good statement, and you can send it to the database. So it has been used, and so it scales to some kind of moderate application. And it's possible to understand how to do it and develop it, because our master students, I was visiting the University of Tsukuba last year, and we had master students in the group, so he picked up how to do it, and he wrote lots of code, and so he understood it, and he defended his thesis in March, and went off to do some consulting work. So it's relatively simple, so graduate students can do it. But of course, the idea was that here example is that it would be very simple. And before I get to the real code, I say there is some ideas that we are going to see over again, and so we'll emphasize it so now, and then point them out as we go along. So there's one main idea of this approach of embedding is that we write interpreters. And we write many interpreters. So we write an expression once and then interpret them many times. Well, it's kind of by necessity, because the whole idea of the style is that there is nothing else you can do but writing interpreters. That's kind of forced to do it. So the second part is that extensibility, and that's one of the selling points. And you can extend in many directions. So you can add, if you have your DSL, then you can add more features to your DSL, and then more expression forms. You have if statements and more features. So that's what you can do. And of course, you can add more interpreters at any time. But there's also the third one, which is relevant to this tutorial, so that you can add more optimization rules. So if you do optimizing, then you add new features, and then you can reuse all the rules which have applied. And you can add more optimization rules. So that's the third extensibility. And of course, everything is typed. So that's the language we embed is going to be typed. Of course, the meta language so Haskell is typed. But it's also interesting that the optimization rules themselves are also typed. And what they do, they preserve, by design, they make sure that all the optimizations preserve typing. So if you start with something of the type, then the result of the transformation is guaranteed to be of the same type. So, which is kind of, it's not, of course, full correctness, but some degree of correctness it preserves. So, the point of this style that we promote to that, it's not maybe for end users, but for using this DSL for some advanced end users. So if you're a compiler writer, of course you don't need these techniques that you know your compiler very well, and then if somebody asks you for new features, then you can very easily to implement. But then you're only one compiler writer, so maybe people ask you for different features and you yourself don't have time for doing all these things. So the whole idea of this technique, how it arose, we wanted to offload these optimizations to users. So the user says, well, I wanted to have this optimization, and this optimization is only good for my specific problem. That usually if you come to like Fortran or C++, C++ compiler, they would not, bother with you, right? Because they only look for optimizations which are applicable, to a wide variety of cases. So if the optimization is to domain specific, it's too much work. Unless you're paying them lots of money, they're not going to do it. So the only way we can do progress, if you're interested in the optimization, you do it yourself. And that's what the style you advocate. So we give you the tools and you write it yourself. But of course, if you are not professional compiler writer, and if you do it from time to time, then operating on a low-level parse tree is very error-prone. And you spend a lot of time debugging it. So at least the point of the style is to, well, not to shoot yourself in the foot, at least, and not too many times. So therefore, there are some errors which are not impossible to, do. So there is something. Of course, it's possible to, you optimize it wrongly, but there are some guarantees of result. And of course, it's called final because, well, it's we'll see why final, but one of the features of the final is everything is in lowercase. So in Haskell, if you write constructor, they're all in uppercase. So if you use deep embedding, everything is uppercase. And stateless final, everything is in lowercase. Okay. And so, of course, we can talk about, all the time, for a long time about these ideas, but, we're programmers, and I wanted to introduce the style, and the only way to introduce the style is just go through the code and see how the code works. And so then for the rest of the tutorial, so just speak on the code and tell you how it is, and maybe we can write some code together. So, as I said, the language is, the domain-specific language is very, very simple. So especially simple at the beginning, so we add more things later on. But at the beginning, we have just wanted to have a domain-specific language for modeling circuits. It's not even actually circuits, it's just very, very simple. You can kind of think about it as wires. So we have a wire which is like literal, so we have true wire, that has Boolean, so it's a wire connected to the ground, which would be false, and a wire connected to the power supply, which would be true. And then we can negate this wire, and then we can feed this wire, like 2 wires into the end circuit, and then would be wire coming from the end circuit. The same thing also. So that's the whole thing. And so if you look at, so it's encoded as a Haskell type class, and if you look at the type class, you can kind of think about it as a grammar for the language, right? So the language has form literal, that, as I said, the wrapper, it means takes expression and returns another expression and another wire, and end wire takes, end gate takes 2 wires and returns other outputs 1 wire. And I shouldn't even bother with Booleans because, well, Boolean, everything is going to be either high or low, either true or false at this point. So it doesn't actually have to bother with this Boolean. But later on, we'll, some other types appear. But for more than like 80% of the tutorials will be only Booleans. And wrapper is the, well, it's a type variable, but it's actually type variable. It's a start of the kind start to start. So it kind of, you can think about it, it's a name of the interpreter to which thing. But so far it says, well, you can, at this point, you can just think about it as part of the syntax. And once we have defined this type class, we can already write domain-specific expressions in our DSL. And this is the first example. So we says literal true, so this is the wire and the high wire, and then the low wire, we negate it, and we can actually end. And if I load it into GHC. Then we can ask GHC, for example, what should be the type of it. And it's a very symptomatic type. It says semantics reparable. So if you see something of this type, it kind of, you can read about it. This is some kind of expression. It's an expression in domain-specific language. And it's going to be return or produce the result of type bool. And it's going to interpret it by, well, by whatever interpreter might implement the semantics for this. But so far, it's, if we have only this language, it's a very boring language because, well, we have true, false, and connect them with end wires, so we want to have something more. And well, to add some more action, then we extend language. So we already do it, so we add 3 more forms. We just add the wires X, Y, and Z. So as you can see, that's and then we can write some a little bit more interesting expressions like this one. And you can see that signature actually, the type context tells what features of the DSL we're using. So this one uses the very basic, so this was expression, a very basic language. And this scene input, that expression is an embellished language. So, and then we can write some more interesting expression. But for example, there is one other thing. And what if we wanted to, well, here is want to encode addition, Boolean addition. Boolean addition is XOR, right? And our language has only AND gates and OR gates. So, what should we do about XOR? Well, I mean, there are 2 things that we can do. So, once we know how to extend the language, we can just extend language once again and add XOR operation. Right? So it would be primitive, a new primitive of the language, and it's very easy to do, and we can do it right away. And I mean, you can think about if you have our toolbox has an XOR gate, then we just treat it as a primitive. But there's another way of doing it. Well, here's some expression using XOR. So this XOR is a Boolean addition, so this adds 3, so it adds 3 wires together. And this one, which I was going to use as an example, so it adds 2 wires together plus the ability to true. So as I said, that we can add XOR by extending the language, but we can also use Haskell itself. So well, XOR is implementable in terms of OR and AND, right? So then we can write XOR is just standard Boolean ways. So you can think about, well, actually we will see it later. So as sort of a macro. So we use Haskell. So Haskell is so we define XOR XY to expand into this expression. So this really is a and that's an advantage of using meta language, that we can easily define macros, and we can also, well, Haskell has some module systems, so we can use modules and separate compilation and so forth. So all the things that come for free. So in our specific language. Well, of course, then, okay, so we can write these expressions, but okay, what can we do for that? So we want to do, at least, for example, to evaluate. Right? So compile them all to do something with it. And so far we can, this is just verifying that we can write them. And the compiler makes sure that the expression, of course, well typed, right? So if we forget some, the wrong type, or forget put AND on the, if I get this operand, for example, with XOR, and then it would be a compiler. So, well, the one thing, well, we write an interpreter. And this is the first interpreter that we can write, and somehow the tradition is called R interpreter. So this is one thing we can do with the circuit is to say if we feed something to the wires, see what's the, what would come out of the output wire. So, right? And well, it's also called meta-circular interpreter, and this interprets all these wires in terms of the corresponding Haskell function. So it's essentially identity interpreter. And if you forget this R, well, for kind of technical reason in Haskell, so R is like, well, it should be maybe new type, is well, it's isomorphic that R of A is isomorphic to A, right? So because you can always, given a value, you can add R and it takes R value, and then if you use eval, then you can remove it, just isomorphic to A. So you can kind of consider. So it means that we always have R Boolean. It means this R Booleans are the same isomorphic to just Haskell Booleans. And well, here, you can kind of see that everything is implemented in terms of Haskell. That negation is then interpreted in terms of Haskell negation, and interpreted in terms of the Haskell conjunction, and we just add and remove this rather R. And for example, we can see that what's the value of the circuit which we wrote, whether it's true, this one. Yeah, and true, yeah, it's supposed to be true. Right? So it's correct. It has to be true. But to evaluate other things, then we need to, so this circuit had only constant wires, but generally we extended things with the X, Y, and Z wires. And now if we're going to evaluate this, we need to say, well, these are kind of inputs, what, that comes out on these wires. And here I just arbitrarily chosen that wire X would be true, and the Z is true, and wire Y should be false. And now we can say, there's X true, I think adds X and Y together. So X and Y, so the results should be good. So it's all true. And as I said that I had so many quizzes that I would suggest, well, I have files on my webpage, so you can go through quizzes and try to see what, do these exercises. But here I would just ask you a question, which is actually open-ended question. So this is kind of dissatisfaction. So here I have true, false, and true. But what if, for example, my input would be different? What if all true? So what should I do in here?
So for example, if we are to implement the input or semantics by a function that taking a couple of booleans, will become sort of, is it possible?
Yeah,
it looks quite straightforward to do that.
Yes, yeah, okay, it's very good. So that's one of the, one of the different ways of adding this, yes. There are other things that you can think about of how you emulate it. If you have, if we, implement this in OCaml, actually, I should have mentioned that, yes, it's implemented in Haskell and OCaml, and these ones actually I personally give tutorials about. But some other people implement it in Haskell, and I heard it's implemented in Scheme, and so I don't know how it's done in Scala. So it's easy. It seems to be easy to implement it in other languages. So in OCaml, for example, there is a what's in here is that class is implemented as a modules, and OCaml has local modules, so which correspond somewhat like local instances, and it would be very easy to implement it through this kind of local instances. So Haskell doesn't quite have it, but we can actually emulate it. Also, I should point it out to this, why it's named into this kind of misspelled way, semantics. So the reason it's named this way, so if we go to the very top, that, as I said, it looks like what you saw, this type signatures, you can think about as context-free grammars, so DNF grammars, right? So this is like non-terminal, so you can see add, neg, lit, and these are names of non-terminals, right? And so this says non-terminal, this is a wrapper, so has, well, and takes, well, this is the, well, the arrows kind of go some different directions. So this is the input and then gets the wrapper Boolean. So it's like a context free wrapper. So it defines the syntax of the language in a somewhat BNF sort of ways, right? So and, so if you, I mean, forget this one, so add says, I mean, expands Boolean, so it's the grammar. So it's kind of a syntax. But on the other hand, so the type class itself is gives the syntax of the next specific language. But this interpreter, which we wrote, it in a sense gives the, oh well, not in a sense, in a very real sense, gives the semantics of the language. Right? So it says that we interpret all these constructs of the language. So how we interpret language? It means that we interpret literal in the literal of X in the domain of R of A. We interpret negation in also X, so every expression interpreted into the domain of, well, in our case, of Haskell booleans. So it gives the denotational semantics of our language. And the denotational semantics, so how it gives us? It says, these instances tell how to interpret the primitive of the language. So how to interpret negation and or. And for complex expressions, then they're just meanings of compose. So we have this complex expression example 2. So what's the meaning of example 2? Is that would be what's the meaning of this one, which is Haskell Boolean true. What's the meaning of varx, which is, well, varx is again probably true. So what's the meaning of negation? That takes the meaning of this and negates it, and what's the meaning of this one that takes these meanings and combines this. So that's what's called compositional semantics, right? So the meaning of each expression depends only on the meaning of it in intermediate children, and what the operation you have to combine. So which is also defining feature of denotational semantics. Denotational semantics usually has to be composition. So what we wrote is to give one denotational semantics of the language, interpret expressions in terms of this domain. And in this case, the domain is Haskell booleans. So therefore, the same class serves 3 different purposes. So it gives the syntax, so the type class declaration gives the syntax, and the different instances give semantics. And we can write many instances, it means that we can give the same expression different semantics. Okay, so that was one of the interpreters, but we can write other interpreters, and that's what I will do now. Is, well, we often not only want to see the result of the circuit, but we want to see what the circuit itself is, so to pre-print our DSL expressions. This is a very handy operation because if you especially do transformation, you want to see what the result of all the transformations. So this interpreter would be very handy. And because it's a pretty printer, well, this one is not a very pretty, just a printer. So we interpret everything as a string. So because we wanted to display it. So everything is interpreted as a string. In this case, what A was disregarded because everything is interpreted as a string. So literals is just literal Boolean true that will be shown true. Negation, it says, well, whatever the X, whatever the string contains it, and I add this squiggle to indicate negation. And for and then or, I would add these operations. And then let's see how it actually works. So for that circuit, then we get true to the false. That's pretty good. So it's again, we wrote expression once and interpreted, we evaluated and it gave us true. And now we pre-print it and it gives us this part. And now we, for example, can this Boolean addition. And now it should be very clear that XOR was the macro, right? Because it didn't say XOR X and Y. Now it's what pre-printed is this thing. And if we, for example, have and if I print this one, then it gives us the XOR of 3 wires, which is a pretty ugly expression. And that gives us this point. Okay, so this expression is a little bit too ugly, and there are too many parentheses. So what what you suggest that we fix this? It's not. It's printing, but it's not very pretty. So if there is any way we can make it pretty.
Optimize it, maybe.
Well, but that's, we optimize it so later comes, right? So what we wanted to do is just to printing prettier, not the, so expression should be the same, but the output should be, have few parentheses.
So maybe that is something
like
you want.
Like a tree.
Oh, that's, yes, that's also a very good thing, And that's not something that, we are going to do it now, or maybe, but it's possible, to, for example, to interpret it as a graph piece. Yeah. So, and then if you output a graph piece, then you can print as a, display it as a graph, which is very nice. So it's very easy. But one of them, if we just want to avoid the parentheses, we'll just do the precedence pre-printing, right? So we don't print parentheses where they can infer by the associativity of parentheses. But now we need to do precedence. So we have to pass each expression is interpreted. So before each expression was interpreted as a just a string, regardless. So whenever true appears in any context, it's just interpreted. Where and appears here in any context, we just put it from x and y and just put parentheses. So that was interpretation was kind of context-free interpretation, right? Regardless of the context. So and expression was interpreted always the same way. Something, put two arguments together, put ampersands between them, and then close in parentheses. But now we want to do something more interesting. So now we want to do precedence printing. So now not always we wanted to put parentheses around and. So we want to depend where and appears in the context. So for example, if and at the top, we don't want to put parentheses around because we're redundant. So this demonstrates that the approach is capable of interpreting things in a context where there are some. And well, how would you interpret in a context? Well, we interpret not as a string anymore, but we interpret it as a function that takes the precedence and, depending on the precedence, do something. So literal, for example, takes precedence and doesn't matter what it is because it always interprets true and false regardless of the context. But negation of, this and I was talking about, now it's done in a different way. So now it takes that p and put parentheses only if p greater than 4. Otherwise doesn't. And puts for the operands, now operands, they are not strings anymore. They are functions that take precedence. So now we need to specify what should be the context in which what should be the precedence in which to interpret the operands. And for them, they go 4. So you can see in this case, if we just have and then together, then should be no parentheses, right? Because it only puts the parentheses when they're greater than 4, but this happened in school. And then or we get the same. So now if this argument of the first, for example, argument of and would be or, it would be parentheses, because now it says it should be in the precedence 3, and or says if precedence is greater than 3, it should be parentheses. So the meaning of this is and is like multiplication, and or is like addition. Right? So that's how parentheses should be. And now we can see how it works. So this part is probably doesn't change it much. Well, the only thing that changed, there's no outer parentheses anymore. And for these ones, it's again, there's this, I think that was the expression was before. Yeah, I think that was the expression. So that was before, and that is so before there were starts with 2 parentheses, and now it starts with 1 parenthesis. So this level it seems to be easier. And as you can see, there was again 2 parentheses in here, and there's 1 parenthesis. So a little bit prettier. And that's a pretty printer.
Excuse me.
Yeah.
How to design a magical number 3 and 4 and 11?
Here I just chose it out of
The order of
yeah, yeah. Well, I mean, here the only numbers is relevant 3, 4, and 10, right?
Yes.
And so in 10 it means negation has the highest precedence level, right? It means that as you put negation and there's something, then actually if it's not primitive, it has to be in parentheses, right? And 3 and 4, I mean, it doesn't matter 3 and 4, you can choose anything, I mean, any numbers, right? So long as that, so one of them, and this has to be bigger than 4, than for the 4. So it means that n has a high precedence, so if or appears as the second or first operand of n, it has to be in parentheses. So that's the only thing.
And how to show that is correct? Since that when you remove remove something, it might change the semantic.
Well, I mean, this kind of changes semantics is that the interesting thing is when you parse it back, right? So what happens? What you would it pass to the same thing when you print it? And so, well, if you parse that, you give the same. That's the kind of precedence parsing. How to correct? I mean, what is a correct? Well, the reason is this is a correct by definition. Right?
Of course.
So it puts this parenthesis this way. So now it's to tell how you actually read this expression back. So right. So what's the meaning if you try to read it back? And then you have to have a precedence parser. And then you need to look at the precedence how to parse it back, and then you get that's what the meaning is. But you can so if I say x and y. So it's in here, for example, I put parentheses in this place, but the way it's printed without parentheses, because well, that's the way the printer is designed. It's associative, and parentheses are not shown. And how associativity works well because of that line. So both operands gets the same precedence. Right? So if you want to have so by implicitly kind of left associative, if you want to associate to the right, then you change the number in here. In that case, you put force of parentheses. So in a sense, this one is a pretty printer. So say, well, this is how we're going to print. Then the question is how we're going to read it back, how we're going to parse. And then, well, you have to look at what you wrote in here and figure out how you're going to parse it. So, but generally, you just write the precedence parser. Or try to imagine what the precedent parser should be in order to read it. Right. But like, for example, if you have AST, then of course it's actually a very interesting question how you design a printer which is correct, and in the case what is correct. That's the way how you go to serialize, how you go to print the tree. Then, well, you choose whatever format you wish, but then you have to decide how exactly you did it, so you can read it back and restore the same tree, so you have to write the parser. So the correctness actually comes in the parses part, in the printing part. So here we have opportunity to divide any precedence and search theory precedence as you wish. Of course, later on when you parse, you can see that what you've done in the printer and then reconstruct with the parser. And writing a parser is also a very interesting thing, because it's actually more complex. Other questions? Yeah.
Can we ask our when we're printing XOR, we get a whole bunch of connectives.
Yeah.
Expanded like macro. Can we make our pre-printer context sensitive, and so that when it encounters an XOR, it printed just XOR, but not that whole bunch of symbols?
Yes, it is possible to do it.
But how does it know that here is the XOR?
Well, I'm gonna kind of look at, try to do sort of kind of pattern matching, right? So if there's two arguments and they feed this pattern of XOR, then we try to reconstruct it back. Well, you have to, what's the context of XOR? This here. It's actually a very good question. Okay, well, it's, yeah. It means it has to recognize whether it, something that is pre-printed looks like XOR. And when it looks like XOR, it means that it has to have X and, connected with OR, and then there's a negation in X and OR. And then, okay, so you do kind of everything that is done matches this pattern, then we can say, okay, that is in XOR. So, if you do how I just said it, then it's possible to program the way that I just said it. So it means in the context you have to keep information what you have just said, what you have just seen, and if you've seen something that matches exactly the same pattern, it's okay, I'll replace it and print it so. But we later on, in the end, we'll see something similar. Not very efficient, but something similar to this idea, where it kind of pretty prints, then looks at the result and says, extract something in the results and use it for, pretty printing again. So for that reasons. It would be at the very end. So it's possible to program this way. Although that might not be necessarily the fastest way, but well, pretty printing usually it's not on the critical path, so that's not something that you could. Okay, I'll point it out. So there's other things that we I wanted to actually do it. Probably I don't do it to save the time. But so, as I said, one of the quizzes is to draw a circuit as a diagram. And it's, well, one of the ways of doing it is just, if you know GraphQuiz, you print it out and don't file GraphQuiz and use the GraphQuiz package, which will draw the trees for you. So it's just getting very handy. So, it's GF tech and this way too. So it's another thing, it's another interpreter we can do, which is very easy to, for example, compute the latency of the circuit, the wire propagation delay. Or because we're not dealing with the physical circuits, but approximation of wire propagation delay. So what's the maximum time that it needs, how many gates the signal has to traverse from input to output. And what's the worst path. Okay, then we determine the performance of the circuits. So that's how we plot figures. Okay. So it's very easy to interpret the circle this way and kind of use the force propagation. So which is and another quiz, which is also think about, as you know, all gates can be emulated if using only one kind of gate, right? It's negative AND or negative OR. So how to compile this circuit to something that we don't have AND and OR, but we have only neg AND gates. So what we represent this way.
So, but suppose we have a function called NAND that just represents the NAND gate, then in our implementation of AND or AND NOT, we just simply code that function with specific patterns, and probably that's all we need to do now.
Well, in a sense, well, I mean, no, but the function, the neg AND is not a function, it's actually a primitive of the circuit, right? So we also wanted to have a primitive.
So we're going to define a new language.
Yeah. So that's the, so maybe I should, so we can consider, okay, let's say 7 NAND. And so we have with N, and it should be equal to and we have NAND, and it will also have only 2 wires, right? So now, so we defined a new language, which has 2 primitives. Again, literal wire, and there is a NAND wire, a NAND gate. And now we wanted to, which is something very similar to DSL, but has a different kind of gates. And now we wanted to transform one DSL into another DSL, so in terms of this one. So, okay, so how we can do it? Well, the only thing is, again, so the answer should be very easy, I mean, so because the only thing that we can do with languages is just write interpreters.
Yes.
So we just write an interpreter.
So suppose the reference.
Yeah, so now we need to say that we wanted to write interpreter such that, okay, so before I do this, I should say we type, so this kind of gives the name of this interpreter, and it would be meant, and I now make an interpreter so we wanted to interpret the primitives of one language, so which is this the language, base language, in terms of the primitives of the new language. So it means literal of X would be interpreted as for example, negation of X would be interpreted, well, so NAND end, that means if we AND of 2 signals, it would be the same signal, and NAND gives an inversion, right? So it should be NAND, and then to do what's NAND of X, right? And let's see if it kind of works. Parentheses. likewise, you should, take, for example, how we implement end. So it becomes end x y. So let's interpret. Okay, so we have NAND that should be, we want to interpret instead of negation of x, instead of NAND, right? So if we have NAND x and y, then it would be negative negation. But we already have a negation, right? So then we just use this one. So now it should be end, right? And the order is the expression. So what happens in here is that we, and then of course we need to write interpreters for R interpreter and S interpreter for those sim language in order to be able to give us and this result. Maybe now it's yeah, maybe it's actually worth working it out and see how it prints it out. But that's kind of the main idea. And I would encourage you to see how it works. But it's kind of now brings us idea to what how to do optimizations. And we see how, why optimization is needed, because if we look at this expression, right, so it's obviously there is a lot of things could be simplified, right? For example, here there is or true. We also know it should be true. We can simplify. There is and true. It also can be simplified. And of course, x and y is repeated too many times, and of course can be maybe simplified this way. But at least this and truth and always true should be to simplify those things. So that's the first optimization is constant propagation, right? So the expressions like and true and or false, that should be able to simplify. And that's what we will. Okay. So the first transformation is it's written this way. So we want to do constant propagation. So if there's applying those rules wherever they apply. So negation of true, end of true of x, false of x. So this means false of x is false regardless whether x is right. And like true of x and true is, again, it's always true regardless of whether x is. So that's a little bit something new that we, well, the last part is already gave us the inkling that we can possibly do that. So before we dealt with the evaluators, so we just evaluated as a Boolean, evaluated as a string, and evaluated as, for example, for the propagation delay, it could be integers, and now we're going to write a transform. So because the result of it should be not kind of similar value, it should be another expression in DSL, right? So we started with one expression in DSL, and we ended up with another expression in DSL. So we transform one expression to another. And so, well, how to do it? Of course, then the answer should be trivial, because the only thing we can possibly do with the DSL written in the style is to interpret. So we just write an interpreter. Now let's, before that, write a very, very, stupid interpreter. Like this one. So it says, so suppose we have a way of representing these expressions, some kind of record. And we wanted to interpret this form into, in terms of this T0. Well, this interpreter, I know, well, you're already laughing because it's very stupid, because it does absolutely nothing, right? So it obviously looks like it's identity. It's actually a little bit maybe tricky to see that there is a neg appears in here and neg appears in here, right? The same thing appears on the left-hand side and the same thing appears on the right-hand side. And you think in Haskell it's always, the danger that this is a kind of recursion. But there is no recursion in here. right? Because this one appeared at different times. So what this one is the expression negation of the language we're interpreting of the kind of, well, T0 language. And this neg is into the expression into this language wrapper, which is kind of new language. It means that whatever this wrapper language is, we are going to give the meaning of our T0 language in terms of the meaning of this wrapper language. And this is done in the most straightforward way, just redirect. And of course, we do the same thing for wireless advice. Of course, this is, as I said, it's a totally stupid interpreter, but it makes a point as how transformation looks like. So what we've done, you can also look at this way. So we are not transforming the expressions in the language. We are transforming the interpreters of the language. So you can view this in the different ways. So this defines not the transformation from one language to another, from T0 language to the wrapper language, whichever wrapper language turns out. But it also, we can look at that from the different side. It takes this wrapper interpreter and makes it T0 interpreter. So it transforms the interpreters instead of transforming the language. And these are the same thing. So it's just different ways of looking at it. But that's the key of the transformation. So in the Tagle's final style, we transform not the language, we transform interpreters of the language. And so we interpreted exactly the same thing, but with a transformed interpreters. And that's the key to the whole enterprise. Okay, so but how are we going to do our constant propagation? Well, that's the same thing the idea from partial relation. And the partial relation, well, in the idea of constant propagation, we try to take advantage of whatever knowledge we have statically without random and propagate this knowledge. Well, at this point, we're interested in constant propagation. So the static knowledge that we're looking at, either if we statically know the value of the wire, whether it's a true or false. So that's the only static information that is relevant for us. So, well, we'll just write it this way. So, the domain of our interpretation, it should be either this, we statically know that this particular expression is either true or false, or we don't know anything about it. Unknown. So, and now we are writing the interpreter in terms of those partially known values. So it means that if we have some information or we don't know information. And of course, if we, before we started, then we can always write a function that's called din or dynamize. This again from the partial relation community. It means if we know something, we can always forget it. It says it takes this wrapper and return this. So this is a wrapper corresponds to no knowledge, right? Because it says it's a meaning of the expression and some interpret a wrapper, and wrapper is just a type variable, and we don't know any. It's a universal quantified variable. It means that we have absolutely knowledge what it represents. So we forget that. So if we didn't know anything, then well, we continue not knowing anything about it. And if we knew that it was literal x and y, then we say, okay, we forget this whatever it, and we interpret using this interpreter. So this way we forget what to say. And now we are writing interpreter, but interpret our DSL into this TCP wrapper. It's a partial value, so either it's known or something which is going to be, so the wire would be either statically known or it's something that's unknown and would be interpreted by this unknown interpreter. So if we have the expression says literal, then well, literal already says this is a statically known, right? It's a true or false. It means this is a static information that we already have. So at this point, we mark it with a literal. So that gives us a static knowledge. Then if we have negation, okay, so if we don't know anything about negation, then we can't do anything. We just say, well, we don't know what it is, and we ask this unknown interpreter to deal with this. And this is the only thing, and it's marked unknown because, well, it's no information. But if we know that it was true or false, then we know what the result of negation right away, without right? So it's believe, and then now we use not Haskell not to complete this result. So this is the propagation information. So we had some static information from the argument, and then we created, figure out or propagated the static information into the result. It becomes. And for AND, well, this is actually essentially the rules that I wrote before. So if we have, there's always a clause. If we didn't know anything, then of course we cannot do anything at all. We just have to ask this another interpreter to interpret what it is. But if we knew that it was true, then of course the result would be E1, and we don't know what this E1. We don't actually have to care about what it's E1. And if the result was false, then the result would be statically false again without knowing what the first argument is. And here it was symmetric. So again, so these clauses deal with the propagating of the static information. What we knew statically about operands, we propagate to the result. And it kind of, the interpreter starts, you can consider bottom up, and it propagates all this knowledge to the whole expression.
Excuse me?
Yes.
Since we are dealing with the symmetric operator,
Yes.
can it be simplified to something much more easier? Because it's a symmetric operator,
Yeah.
so the rules are redundant. If we have something can indicate the symmetry characteristic.
Well, we
Well, I guess we could just call the original
Yes.
for TCP.
yes, we can make a help process do it kind of symmetric.
Maybe we always put the literal into the first operand.
Yes, and then
So-
switch the arguments.
Yes, yes.
If it's, well, yeah, so if we, and then look at if it's unknown, for example, right, and then switch the arguments.
Yes.
Yes.
Maybe.
And of course, where unknown here comes in. So here literal comes in from literals. And unknown comes in from this wire x and y in, right? Because these are our interpretation, these are some kind of unknown wires. So we don't know what the static of the value is. So then we mark them as unknowns. And so as I said, everything gets propagated, and let's see how it works. And at the top, we just forget all the static information because static information was only needed in the process simplification, and we extract the result. And let's see how it works. So this, so let's remember that was original circuit that was x and y and x plus y plus 1. Given particular assignment of x and y. So it gave us this value. So we interpret it as a just using evaluate, and it gave false given some particular assignment of x and y. And we interpret it now in a different interpreter, which is view, pretty print, and that's what it is. And what we've done now is apply this. We now define a term underscore CP, which says applying this operation of CP. So interpret this this term, which I just printed it out using this partial evaluation. With type of this. So the type says, well, it looks like it's again expression in our DSL. So and xz1 was also expression in our DSL. So it looks like we have started with one expression in our DSL and get another expression in our DSL. And it's polymorphic record. It means that we can interpret this result many different ways. And this is an example I would show how to do it. So we, for example, can evaluate and it will likely gets the same result, false, which is not the sign option. It's supposed to be optimization. And we can pre-print it. Well, then it looks much better than before. So this one, and now this property is. Yeah, it's indeed, I mean, you can see y and true, so that has to be true, right? Mm-hmm. And then n is true, so I mean the whole term gets disappeared. So it should be x, which is what remains. And here we have not y, again, that's not true. So this part disappears, so it should be negation of the parameters. Looks like it does work. So, to reiterate the point that what we have done, so again, if we look at this line, we can think about that we transform one expression to another. We had one expression of the type so we had expression of the type, and we ended up with another expression of this type. So again, this type looks like, if you see this type, it means it's encoded a DSL expression. And if you see this type, we just have exactly the same, it's encoded a DSL expression. So, I mean, from this line, we see we transform one expression to another expression. But if you look at what we've done, how we've done this, then it's done by transforming the interpreter. So if we say, if we have the interpreter for the target language, for the simplified language, then we can write an interpreter for complex language. So this wrapper would be interpreting only simple expression, which will with constants only. And this interpreter is interpreted expressions without constant combination. So by this line, you can see we transformed an interpreter. But these are the same, these equivalent ways of looking at this. You can think about transforming expression, and the result is that's what we want to do. But how we actually accomplish this, we are writing the transform the interpreter of one. And that's how we do these operations.
Excuse me.
Yes.
How do I know there only takes one parse to make it the simplest expression?
Oh, I mean, you don't. I mean, and then eventually you'll see that it's, you don't generally.
Yes, of course. So.
Yes, and then we are coming to this. Yes. Generally, I mean, well, the way how you also do optimization is that, well, for this particular thing that we know that how to do it in kind of a one pass. But in general, when you do simplifications in general, then you iterate until you get a fixed point or until you run out of patience, right? So you do it like 5 times and then you say it's okay. So that's how
it's smaller than.
Well, how you do it in compilers, right? So in GHC that does these things and then run simplify 5 times, then does some other information and again run simplify 5 times, and that's how you do it. And that's well, at the end, when we get to it, then you can do exactly the same thing in this frame. Yes, you can. But before, now, so we know we can do it. But of course, the question is, well, what is kind of dissatisfaction in this? There is a little bit too much boilerplate in this. And to make it a more interesting framework, we're going to eliminate all this boilerplate. And one of the things is one particular boilerplate, one operation that we kind of keep doing this is that this dynamic operation. So it means that given some information, we forget it, right? And in this particular, it's kind of often appears, well, okay, so one pile, in one that's, the main idea of the framework will be always this way. So we have in particular static information, and we interpret it in this domain that says either we don't have any static information or we have some annotations. So we are going to be adding, when we program other transformations, we are going to be adding different annotations, whichever needed for the optimizations. But once we added annotations, we always have this operation in which forgets all the annotations and gets unannotated terms. And of course, we also have operations like this one, unknown, is to add annotations. In this case, adds dummy annotations. It means we just says we have no idea what this is. And so this is kind of a boilerplate, and to optimize it out, we introduce a framework of this one. So we define a type class which captures the common pattern. And the common pattern says that if we can kind of read through this. So if we have annotated term, you can forget annotation, so kind of go backwards. And if you have unannotated terms, then you can add, well, you can go forward, but it means you can add no information whatsoever. So it just adds dummy annotations. And that kind of from forward and backwards looks like their identity, and in some cases they do. So if you add some information, dummy information, and then immediately forget it, then it of course has to be identity. But the result of course doesn't hold, right? Because here backwards it means that you can forget meaningful information, and that's you're going to get a dummy information. That's not the same as was before. So that's part of the identity. So it's a that's called the reflection reification pair. So that the functions forward and backward, they're not exactly identical, inverse of each other, but they satisfy them. And this map 1 and map 2, there's the primitives that kind of, if you have, if you want to apply operations that takes unannotated terms, and you want to lift that operations into the over annotation. So what you do is first you get the annotated terms, you forget information, you apply this transformation, and then you add them in. So you kind of work around. Then map 2 is and this is going to occur very frequently. That's why they are separated out. Okay. Now we do something more interesting. So so constant propagation was partial evaluator. So this was indeed implementation of partial evaluation, which you can read in the textbooks. So by meaning evaluator, it kind of looks like it's evaluator. So the question is, can we write something that is obviously not evaluator? Because all this, our interpreters, evaluator, pretty printer was definitely evaluator, this partial evaluator is also evaluator, so they're all evaluators. So evaluator is something like a fault, right? So performs folding on the tree. And that's what people kind of, or you can also think about as a context-free rewriting. So it performs the same sort of information like fold does, perform operation regardless of the context. And so the biggest question was that could you program operation transformations which do not look like a fold at all, which depend on the context. So that was actually a very interesting question, is that in general, so the reviewers of our first paper that pointed out how can you do something that's, what you implement is like you implement the fold, can you implement something that is not a fold at all. And here we wanted to do one transformation, we wanted to do double negation elimination in the electrical sense. So two negation each other, then we should cancel each other. So this is an example of a non-context free transformation. It means we need to look at negation when it occurs right in the context of negation. Or in other ways, we can, well, it's very easy to do it if you do pattern matching, right? So if you look at the thing, if you see neck, and you know the argument is neck, then eliminate this. So if you encode this in a standard data type style, it's very easy to write this transformation just through less than pattern matching. But how to do pattern matching in this style? So when I first mentioned this style, it was in a DSL conference in Oxford in 2009. And there was one very old professor, and then he immediately, when they started talking about it, he immediately said that, isn't it bloody obvious that you cannot do pattern matching in this style? So my answer to that, which I'm going to show, that it's, well, first of all, it's you can do transformation in this style, and it's not obvious, and well, and it's not bloody. So again, how we're going to do it? It's very easy. So the only thing that we can do is by writing an interpreter. And I wanted to impress. There are actually many other ways of implementing this, and originally I implemented in a much more elegant way, maybe more insightful way. But what I'm going to show now, it's a dumb way. It's much less insightful, but on the other hand, it's much more mechanical. So you just get the idea and very boring way applying it. So that maybe, not maybe satisfying, but it's because it's systematic that we can do it even with your time. And no creativity is required. At least in this case, it's good. So the approach is the same thing that we had before. So we are going to annotate, to transform into annotated terms. And annotation, which we care about, whether again, we wanted to eliminate double negation. So it means that we are going to interpret negation differently if it occurs in the context of negation. Right? So therefore, the only thing we care about whether something is negation or not. So we can eliminate it. So that's why the only information we care about is whether it was negation or not. So our interpretation domain is something that we don't care about, so that line is always present. It's unknown because we don't care about what it is. Or what actually it is, it's a negation. So here, a wrapper is the interpreter for the optimized language. So it says that this is some expression, unknown expression, and it was a negation. So it was a negation of some expression. And that's. So how we interpret lit? Well, for lit we say, well, we don't care about it because it's definitely not negation, we don't care about this, so we just said unknown. But we have this forward thing that forward is the same as unknown. I think later on. Oh yeah, here it is. So to use our framework, I would define a reflection and verification pair on this domain end to end. So forward, it means adding dumb information, and something that we don't care, so unknown. And backward, it says if it's expression we don't care about, well, we don't care about. And if it was a negation, then we use the interpreter to negate it. So it was a negation. And the rest of it is just as simple. So for and for, we don't care anything about what they are, and so we use this map2 function, which propagated that information. And we only care about whether it was negation or not. So if it was a negation of some kind of unknown thing, then we say, well, it was a negation of some unknown thing, marked with negation. And it says if it was a negation of something already negated, well, that's what our case we can do optimization. We say, well, we eliminate this neck and mark it just. And that's it. So once we build the expression, we have some static information whether we saw negation or not. And then we saw negation, we mark it negation. And then when negation says, well, we previously saw the negation, then okay, well, that's what the transformation says, eliminate it. And that's it. And let's see how it works. So if I here is the sample expression, and I will just view it. So I'll view it, and if I try to eliminate negation, well, it looks like it did. And now we see what happens with our term. Well, it might look, I mean, it's somewhat simpler, but there is also, obviously, there is a double negation. There is this one leg, right? And if you look at that, there's a, I mean, there's another leg. So there is some double negation. Okay, so here it is. Okay, so this one is its expression parenthesized, this is a negation. And inside, if we look at it, there's another negation. So there is some kind of double negation. But we didn't eliminate it, right? And the reason it eliminate because what the rule says that we eliminate if they're next to each other. And these are obviously next to, not next to each other. So what we have to do is then we have to bring them, close to each other, and then we can eliminate it. Yeah, so we need to apply another transformation. So before we try to eliminate negation, we have to push it down to the literals. And once they actually hit the literals, then we can eliminate. And that's what we just said. So we want to apply this transformation. So if we have something, then we push it down. Again, there is a way of doing this much more elegant and also much faster than what I outlined, because this one is it's really slow. But on the other hand, this is a very dumb. And this is a good thing in this case, because you don't have to think about how to program it. But it's very systematic. Again, we want to do this transformation. It means that when we interpret negation, we need to look at what we're interpreting, whether it's what we're interpreting is and, or whether it's interpreting or. And in other cases, we don't care. So we define the in language in our interpretation domain this way. So there's something that we don't care, and there's something that we do care. And we do care in this case whether it was or whether it was and. So we say, well, we saw some connectors which is O and N. Here is the argument of it, and here are the argument of these connectors. So these are exactly, so we keep all the information which relevant to us. And this kind of looks maybe similar to what people say deep encoding, because we represent things like a data type. It almost looks like AST. But it's not quite AST, right? So one of the part is why it's not AST. If we do AST, then we need to have connectors or constructors for literal and for negation and so forth. But here it doesn't actually have. So we only designed this data type to keep any information that we want to have, and nothing more. So we design every optimization has its own data type that collects whatever we want. And again, this is a very, very straightforward. Again, the same idea applies over again. So backward transformation, if we forget information, if we're going to forget, if we didn't know anything, that we continue not knowing anything. If we saw it was and, so we interpret as an and. If we saw or, then we interpret as or. And this is the only one line which is, well, now. So we don't care about literals. We don't care about y or z. And if we saw and, we mark it. We saw and. If we saw or, we mark it. We saw or. And negation does implements the rules that we outlined. So if we saw something that we don't care about, well, just use this interpreter, wrap interpreter to negate it. And if we saw something with some kind of connector C, then we flip the connector C and negate the arguments. So push negation. And at the end, we just forget all the static information because it was only needed for the. And let's see how so that part, it's original term, which is x plus y plus 1. And now we eliminate, try to say push negation down. Okay. That neck got pushed down. Obviously, there's some got pushed down. So in here, that's went to all the way. So it's instead 3 points. But here it doesn't actually push down too. So it moved a little bit, but here
Why not?
quite, I mean, you need to do more.
Oh.
Do more.
One step at a time.
Yeah, so it does, I mean, it's implemented it's deliberately implemented this way, one step at a time, so precisely. But, I mean, because it looks like it's an interpret of, transforms one term to one term, why not to do it, several times? Well, we can do it, several times. Well, now we got, this part, this negation got, further down. And if we do it 3 times, then in this, for this expression, it went all the way down. Okay, now it pushed all the way down.
But how do I know I should stop?
Well, usually the way you do it, if you reach a fixed point, right?
Yes, of course.
So you keep doing it until
Okay.
it's, nothing changes. Oh, right. So.
But how do you prove there's a fixed point?
Oh, in general, you don't.
Of course.
Well, there isn't. For some of, well, it is generally complex things, right? So, so if you have a set of transformation rules, then there is a whole area of writing systems as if the writing system terminates, right? And there is a lot of people do a lot of research in exactly this area, whether it's a terminating the writing system. But generally speaking, a lot of these optimizations are not terminating. Right? Because, well, for example, if you have commutativity rule in your system, then you can flip this commutativity all the time, right? So you never terminate. So therefore, you have to. Well, of course, there are other things like Knut-Bendix things, ordering, how you try to, simplify it. But generally, it's a very big research area. So for some systems, you can find the ordering, and when you apply the transformation, then you say, if you just do it as many times, eventually you reach this point. In some cases, it's not possible to do it, and in some cases, you don't actually care about, you simply say, well, do it 5 times, and it's good enough. But you can also program in this way that they just say, if you think that, the fixed point exists, you can simply say, well, I'll iterate until it exists.
But in these types of program, the types are not the same, and how many times we can do it depends on how many times the RR end-to-end layers are there.
It's very good. Yes, very good. Okay. Very good. Okay. I'll come back to it. Very good question. Okay. So now we wanted to. So we know that things can compose, and let's try to see how we can compose them several times. So we know how to compose this down transformation eliminating down, right? And then we had another transformation. We said negation elimination, and we had another interpreter that says do the constant propagation. So for example, if we look at this interpreter after the constant propagation, then it looks like this way. And now we can, there is some negation in there we can push down. And so if we, what I've done is, well, okay, so it's in here, I put double negation elimination and then push down, right? So, and if I do it in a different order, because then the result would be was different. Then the result would be different because this one gets eliminated. Because first I have to push things down and then I need to eliminate. So if I start eliminating and then push down, then it may be separated and then they remain. So of course that depends on which order transformation applied. That's very kind of obvious, so it's not a confidence system. But we wanted to, one way of kind of getting around this is just do it many times. And this is exactly what was the question is, how to do it many times. And this is what it says. So, well, there is a way of doing it is, well, there is a process called polymorphism. Then that's what. Yes, it's indeed, it goes in the different types, but you can say all so this, we've done this. And now if I say n times, so if I, and let's use this chain one. So now if I use this old expression, and now I say, take this optimization chain one, and chain one, it says, take all our optimizations together. So, and this is actually not a very good rule. So it first says, eliminate negations which are adjacent, and then push negation down, and then do constant propagation. So that's usually not the smartest way of doing it, right? So usually you probably want to do it in a different way. So first eliminate, do constant propagation, then become simpler, then you want to push things down, and then you want to eliminate double negation, because then after you push down, then probably will be close. So this chain one is, the opposite of the previous thing. But we don't care because we repeat it several times. Well, it looks like it does all the things that in my head. So it eliminated true and false and pushed everything, negation towards the bottom up and eliminated all those switches. Of course, here there are other things. Then this chain one is kind of baked into this n times. So how to abstract it? It's a little bit more complex, and you can actually do it, but think about it. It actually turns out much easier to do in a kernel than it is in Haskell. Okay, so obviously that one of the things that you're probably asking and where it's actually going, then how can we do ultimately test? How, for example, convert an expression, the conjective normal form and disjunctive normal form. Because we already kind of done it, right? Because pushing negation down is the first thing that we do in the conjective normal form, right? So only, and eliminating negation, so only literals negated. So the next thing to transform the CNF, we need to redistribute conjunction as disjunction, so it's only disjunctions at the top, or conjunction top and disjunction next to it. So now we have to apply distributivity laws of conjunction and disjunction. And it's actually would be a good exercise to think about how we can proceed. So during the tutorials, Vancouver actually went through this, but we don't have time, so this is the last part, which will be more interesting. So before, things were just wires. So you can consider all this wrapper represented as simple wire. And now we wanted to make a circuit. So the circuit has some inputs and some outputs. Well, in this case, the circuit has only several inputs and one output. And it kind of, you can think about it, lambda abstraction is kind of the way to think about as a circuit. So it has input, and it has only one input and one output. And the body of this abstraction is some combination of gates. So you can think about lambda abstraction is a representing one circuit, or a combination of circuits. And operation, the inverse of the application up, you can think about it as connecting two circuits, not wires, but two circuits together. So you have something, or connecting this wire to this particular circuit. So the function is represented as a circuit, you connect wire, and you get another wire. So connecting the results. So that's how high order comes in. So that's what we add new operations to our language, so to be able to talk about circuits with input and outputs, and not just gates, but combination of gates. So we add lam, and so we extend our language again with these operations. This is just extension, right? So all the previous operations that of the language was there, so all apply, but now we add two more operations without even mentioning the other operations which were and or and so forth. So one of the things interesting to note is these signatures of lam and up. They look like typing rules of the simple type lambda counters. Right? So it says if you assume under assumption using actually natural deduction. So if you assume something of the type A and you can derive B, then it means that you implication from A to B holds. And if you prove that A implies B and you have some A, then you can prove B. So it's a type of rules of simple type. I mean, you can read it as a logical. It's a natural deduction of the simple type of the counters. So which is another way to. Another advantage for tagless final is that these signatures, they look like a type system. And therefore, your Haskell becomes the type checker for DSL. So before we had only simple types, only booleans, and now the types become different. So now we have function types, which define the circuits. And Haskell would let us write only the well-typed terms, so it would let us connect to circuits which has an appropriate number of, like you cannot say and to the circuit, right? Because you need to connect wire to it before you can connect to the end. So now we can write addition in a better way of this operation that adds three numbers x, y, and z. So before x, y, and z was something that has y, x, and y, and z kind of, so kind of you can see kind of breadboard, and so say x, y, and z, there's inputs. And now it's a circuit that has three wires coming together, and there's one wire out. And so you can see. So if I look at the type is, the inferred type is says this is a circuit that takes three inputs and returns one. I didn't write any type annotations, so the Haskell itself figured out. So the Haskell becomes the type checker for our language, which is kind of nice advantage that we don't have to write any type checker, type inference. Actually, not only type checking, it actually infers this type. So we use the Haskells for type inference. And again, we don't have to write it. And this is the simple the example when we had adding two wires together with a true. And if we see what the type infers, well, that's kind of infers using the type. It has two wires and the Haskell. Okay, so that's closing. So now we extended the language, we need to extend our interpreters. And the interpreter R was very simple. It was just identity interpreter and it remained identity interpreter. So it means the Haskell, there's a circuit which is a function from wrapper, just becomes the Haskell function. So I don't want to unfortunately, I meant to address your question about this XOR. And this line, this part of the line, this part actually answers your question. But I guess we have to talk, afterwards about how it works. But yes. And the point of this piece of code that now we have functions, and now when we wanted to print a function, we want to print function with some kind of variable names. But how are we going to get variable names when there's several functions, right? And of course, we can say we need to write an interpreter, but on the other hand, we can't, because interpreter S, well, we can has a kind of state monad and pass this counter, variable counter to it. But on the other hand, we want to extend S interpreter, and S interpreter didn't have a provisions for any state monad. So, and here's the idea how we can get around the problem of generating variable names. And here just simply show that how we can view this. So if we view, for example, this is how the circuit that takes 3 inputs and produces their sum. So as you can see, it figures out X, Y, and Z's. It's assigned the names so that it chooses that name for this. And this one is. And this one was, you can see from its type, it was the same. It was the circuit, and then so it takes 2 inputs, but it took the previous circuit with X, Y, and Z components and applies V. The first would be V, another was U, and the third was true. So it kind of the circuit says we take one circuit and then connect the wires and have a bigger circuit. So you put one circuit inside of another circuit, and just saying that one wire would be true. So that's the idea of this, how to read about this. That's why there is application. And well, now we have added more things, but we want to, that circuit, of course, was very, very inefficient, because this one, there's lots of, well, there's a true, so we obviously can do some program transformation and constant combinations. So how we can simplify circuits instead of gates? Well, we already wrote, spent most of the time simplifying gates, and now we have circuits with ups and downs. Well, we now have to say, we have an extended language, which is SIG and O, but we have interpreters for the previous language. So we now need to say that these all the transformers, they apply for the extended language. But all this transformation dealt with negation and elimination and so forth. They didn't care about applications, right? Because it was relevant. And so the way that we extend, we just add this, well, for M, we use this function map2 and so forth. Simply propagate this information through them because they are relevant for the transformations. In OCaml, it's actually possible to even avoid this boilerplate, but in Haskell, it doesn't seem to be, well, at least simpler to avoid it. But it's very mechanical, so it's impossible to do it. But surprisingly, that's all that's needed to do. So all this transformation that we spent so much time eliminating negation, now will be applied to our circuits. And here, for example, so if as you can, I can apply this pushing negation down, but now we're applying it to the circuits, not to the gates, but to the circuits. And you can see now we push some of the negations down. And I can apply it several times, for example, here. And this one's push down, and I can eliminate this double negation. Get the simplified circuits. So what happens is that all the transformation that we program, they apply now exactly as they were. So I don't have to write them. I only need to say that in the extended languages, this new thing that I added, they're irrelevant. And that's what it is. But there is some slight dissatisfaction. So in this case, it did some transformation, but we wanted to have something more. We wanted to have this application applied as well. So we wanted to eliminate the application. So we want to have extra transformation for high order, which is specifically for high order, which didn't exist even for the bits. So we kind of wanted to merge. And this is the last case that we have to be fast. So how are we going to high order constant propagation? So we wanted to have, if it's a function, if it's a lambda, then it's kind of statically known lambdas, and then we're going to substitute. It's a little bit more complex, but the idea is exactly as before. So we want to apply the transformation. So if we have an application to a statically known function, and statically known function means it's a syntactical lambda, then we are going to apply this function. So static knowledge if we've seen lambdas. So it means if we've seen lambda, then we know it's 1. And otherwise we don't care. And that's the whole transformation. So if we say, if we've seen lambda, then it means it's well, we've seen lambda, then we mark it. And now application does a transformation. So if we've seen lambda fun, so it was application to a statical known function, we just apply this function. And that's it. And for other cases, we don't care. It is a default. And unfortunately, again, in Haskell, we have to write it, but in Makam, we don't have to write this part. And again, if we do all this transformation, now we have even more transformation. So we have down, negation, constant propagation, and high order constant propagation. And if we do it several n times, for example. So let's see how it works. So if I started with this complex expression, and what I ended up is 3 times all the possible transformation that we done. We got this some kind of dump order. So if I do this, then it looks much better. Okay, so that as I said, that I've done it for 3 hours and a half. So I can obviously go further than that, but we can for today probably should stop at this point. There are should probably point out there are more things that you can think about it. That you can. Here we have circuits which we have several inputs, but only one output. Most of the circuits have also many outputs, right? So how to add it to this language. And think about implementing CNF, as I always said. One of the interesting transformation, but there may be other things like this one, and this is important. Then how to deal with sharing, which are very, very interesting things. And maybe full-blown circuit pulling and circuit simplification. So, although it's very, very simple thing, but you can take it very, very long way around. So you can implement real hardware design language this way quite easily, so you can kind of see where it goes. So it's possible to take it much further than that. But I hope that I gave you some flavor how it goes. And not only, also I would encourage you to think about maybe more creative ways, so all this simplification can be done much more creatively, but then you have to think about it. But in this framework where you don't actually have to think about that much, there is only one idea, is that propagating static information, figure out what the static information you want, and then code in a data type. And after that, it all becomes mechanical. And that was kind of idea to make things done. So you just don't have to think too much about it. Apply this way. That's it. Thank you.
I think actually now is already time for free discussion. So maybe if you have any questions for Oleg, you can just approach him and ask him. Okay, so thank you. And thank you.